Think about light from a distant star, one that's millions of light years away. For all that time, for millions of years, a particle of light has been flying through the absolute emptiness of space, crossing an unimaginable distance just to end its journey by landing in your eye. But what if I told you that for that particle of light, its incredible journey took no time at all? That all from its perspective, the moment it was created and the moment it arrived in your eye happened at exact same instant. And that the millions of light years of distance it crossed was for it precisely zero. It's a conclusion that sounds completely impossible, like it violates the most basic rule of reality. A journey of millions of years is not instant. A distance of trillions of miles is not zero, and yet this is a direct, unavoidable consequence of one of the deepest truths about our universe. A rule so powerful that the space and time themselves will literally stretch and shrink to make sure that this rule is never ever broken. To understand this, we have to see the universe not from our perspective, but from the perspective of light itself. And what we'll find is one of the most profound ideas of all physics, that for light, there is no space, there is no time. Before we can break the rules of reality, we need to understand the rules we live by. Our whole lives are built on what feels like an obvious truth about the space and time. Imagine you're standing in your room and you want to walk to the other side. You know without thinking that this will take some amount of time, a few seconds maybe. You know that you have to cover certain distance, a few meters. This relationship is simple and predictable. Speed, as we have learned in school, is just distance divided by time. This intuitive view of the world was formalized centuries ago by Sir Isaac Newton. For him, space was an absolute, unmovable stage where everything happened. A meter was a meter, no matter where it was. Time was a universal clock, ticking at the same rate for everyone and everything. It flowed like a great river, carrying all of us along with it. This is the world of classical physics. And for just about everything in our daily lives, it works perfectly fine. For example, if you are on a train moving at 100 kilometers per hour, and if you throw a ball forward at 20 kilometers per hour, someone in the platform will see the ball zipping by at 120 kilometers per hour. The speeds just add up. It's common sense. For centuries, everyone assumed this simple addition worked for everything, including the fastest thing we know, speed of light. The thinking was if you were on a spaceship moving super fast and turned on a flashlight, that beam of light would travel at its normal speed, plus the speed of your ship. It seemed obvious, it seemed logical, and it was completely wrong. In late 19th century, physicists were grappling with Maxwell's brilliant new theory of electromagnetism. Buried in his equations was a startling prediction. The speed of light in a vacuum was a constant. It doesn't matter how fast the source of light is moving or how fast you are, it's always the same number, about 299,792 kilometers per second. This created a crack in the foundation. How could the speed of light be same for someone who is standing still and for someone chasing it at half its speed? It violated the simple logic of our train and the ball example. This simple and stubborn fact, the constant speed of light, would force a complete demolition and rebuilding of our understanding of space and time. And the architect of this new reality was a young patent clerk in Switzerland named Albert Einstein. In 1905, Albert Einstein published his theory of special relativity. It was built on two ideas or postulates that sound deceptively simple. The first one is the principle of relativity. It just says that the laws of physics are same for everyone in uniform motion. Now, this is basically just an extension of our intuition. If you were on a perfectly smooth train with no windows, you can't do an experiment like throwing a ball or pouring a liquid that would prove that you're moving. Laws of physics work the same, and only your motion relative to someone else matters. The second postulate was a bombshell. Einstein took Maxwell's weird result and ran with it, declaring that the speed of light in a vacuum is same for all observers, no matter how they are moving. This means that if a rocket flies past you at 99% the speed of light and turns on a laser, both you and the pilot will measure that light beam traveling at exact same speed, the cosmic speed limit, which is the speed of light. This is where our common sense completely shatters. To accept both these ideas, something has to give. If speed, which is distance divided by time, is absolute for light, then the distance and times themselves can't be. They have to be relative. They have to stretch and shrink depending on your motion. This was Einstein's revolutionary leap. He realized that the universe doesn't have a master clock or a master ruler. Instead, it has a universal speed limit, and the fabric of space and time will warp in bizarre ways to make sure that no one ever breaks it. What we experience as space and time are woven together into a single thing, space time. And this fabric of space time gets distorted by motion. To wrap our heads around just how weird this is, we need one of the physics' most powerful tools, the thought experiment. Imagine a clock, not just any clock. This is a light clock, the simplest one you can imagine. It's just two mirrors facing each other with a single particle of light, a photon, bouncing between them. Every time the photon hits the bottom mirror, we count it as one tick. Simple enough. Now let's put the clock on a table in front of you. You watch the photon travel up to the top mirror and back down. Tick, up, down, talk. The distance is fixed, the speed of light is constant, so the time for each tick is perfectly regular. This is your clock at rest. But now let's put that same light clock on a transparent spaceship and watch it fly past at say 80% the speed of light. For the astronaut inside, nothing has changed. According to Einstein's first postulate, the laws of physics are same for her. She sees a photon going straight up and down just like you did. Her clock is working normally. But what do you, the person on the ground, see as the ship zooms by? You don't see the photon going straight up and down because the clock is moving sideways. So you see the photon travel a longer diagonal path. It has to travel up at an angle to hit the moving top mirror and then back down at an angle to hit the moving down mirror. But here is the mind-bending part. Both you and the astronaut have to measure the speed of light, or speed of photon in this case, adds exact same value, the speed of light. And that's the unbreakable second rule. But you can see the photon take a longer distance, and if speed equals to distance by time, and the speed must stay the same while the distance has gotten longer, then the only possible conclusion is that the time for that journey must have gotten longer too. This means that from your perspective, the astronaut's clock is ticking slower than yours. While her clock goes tick, your might go tick tock, tick tock. Time itself has slowed down for the astronaut and her spaceship. This isn't a mechanical glitch or an illusion. It's a fundamental property of reality. This effect is called as time dilation. And it's not just a theory, it's real. We see its effect every day. GPS satellites, for example, orbit the Earth at high speeds, and their onboard clocks run slightly slower than the clocks on the ground, just as Einstein predicted. Scientists have to constantly correct for this. If they didn't, your GPS would be off by several kilometers every single day. We also see it in particle accelerators. Short-lived particles called muons, when sped up to near the speed of light, survive far longer than they normally should have. Because from our perspective, their internal clocks have slowed down. The faster you move through this space, the slower you move through the time. This effect gets more and more dramatic as you get closer to the speed of light, approaching infinity. But what happens if you actually get to the speed of light? Well, we'll get there, but first, we need to look at the other side of this strange coin. If time can stretch, what happens to space? Einstein showed that the space and time aren't separate. They are woven together in a four-dimensional fabric called space-time. You can't mess with one without affecting the other. The light clock experiment showed that moving through the space shows your journey through the time. So it stands to reason that it has to affect your journey through space too. Let's go back to our spaceship. For the astronaut moving at high speeds, her time is passing more slowly than yours. But to her, everything feels normal. In fact, from her point of view, it's you on the ground whose clock is running fast. Relativity is, well, relative. So who's right? You both are. Your measurements are equally valid in your own frame of reference. Now, this symmetry leads to another bizarre result. To keep the speed of light constant for everyone, not only does time have to dilate, but the space itself has to contract. From your point of view on the ground, an object moving at relativistic speed will appear shorter in its direction of motion. Now, this is called as length contraction. Imagine our astronaut is flying a 100-meter long spaceship. As it zips past you, you'll only see its clock ticking slowly. But if it measure the length of this ship, it will be less than 100 meters, maybe 80 meters or 50 meters depending on its speed. The spaceship has physically shrunk, or at least from your perspective. The astronaut inside, however, wouldn't notice a thing. To her, the spaceship is still 100 meters long. But if she were to measure the distance between 2 points in your stationary world, she would measure that distance as being shorter. And again, this isn't a visual trick, like something looking smaller in the distance. It's a real physical contraction of space itself. The universe literally rearranges its spatial dimension from your point of view to guarantee that you will always measure the astronaut's headlight beam traveling at the speed of light. The faster something moves, the more it contracts. And just like time dilation, this effect becomes extreme as you get closer to the speed of light as the universe in the direction of the travel starts to flatten. So now we have two key results. The faster you go, the slower time passes and the shorter distances become. Now, what happens if we take these two ideas to their absolute limit? What happens if we try to imagine the perspective of light itself? We are now ready to take the final leap. Imagine you are created in a core of a star in Andromeda galaxy, some 2.5 million light years away. Your destiny is to travel across intergalactic space and end your journey by hitting an astronaut's eye on Earth. From astronomers' perspective, your journey takes 2.5 million years. For 2.5 million years, you cross an incredible distance at the constant speed of light. But what is that journey like for you, the photon? First, time dilation. The math shows that as you get closer to the speed of light, your experience of time slows down, heading towards zero. At the actual speed of light, time dilation becomes infinite, which means that for you, the photon, time stops completely. The moment of your creation in Andromeda galaxy and the moment of your absorption in the eye on Earth are not separated by 2.5 million years. This happens at the exact same instant. For you, no time has passed at all. And second, length contraction. The formula for length contraction shows that as you approach the speed of light, the universe in your direction of travel shrinks, heading towards zero. At the speed of light, this contraction is absolute. The 2.5 million years of distance between Andromeda and Earth shrinks down to nothing. From your point of view, the distance you traveled was exactly zero. So let this sink in. From the perspective of a photon, its journey across the cosmos is both instantaneous and covers zero distance. It is emitted and absorbed at the same place and at the same time. For light, there is no journey, there is no duration. Now, to be fair to the physicist watching, there's a technical glitch. Strictly speaking, a photon can't have a perspective or a frame of reference. A reference frame is a viewpoint where you are at rest. But one of the core rules of relativity is that light moves at the speed of light in all reference frames. So, nothing can be at rest with a photon. So, talking about what a photon experiences is a conceptual shortcut. It's what the equation shows us happens in the limit as you approach the speed of light. It's the logical, unavoidable conclusion of the rules that run our universe. This strange, timeless reality of photon isn't just a mathematical quirk, it points to a fundamental nature of space-time itself. Einstein's theory showed that while the different observers can disagree on how much time or space separates two events, they will all agree on something called space-time interval. For any two events connected by something moving slower than light, like you walking to the office, we call the interval as time-like. Cause and effect are possible. There's a clear before and after. For two events so far apart that not even light could travel between them, we call the interval space-like. They are causally disconnected. Like Cuban Missile Crisis and the birth of a star in another galaxy on the same day are space-like events. One could not have caused the other. But the path a photon takes is special. It's called as light-like or null interval. For any path light takes, the space-time interval is always mathematically zero. This is the real physics behind the statement that for light, there is no space and no time. Its entire existence, from the emission to absorption, traces a path of zero length on the fabric of reality. We can visualize this with a light cone. Imagine a star exploding. The light from that blast spreads out in a sphere. If we graph this on a space-time diagram with time going up and space going across, that expanding sphere of light forms a cone. The surface of this cone represents the path of all the photons from that explosion. It is the boundary of causality. Anything inside the future light cone can be affected by the explosion. Anything outside, it cannot. The photon itself travels along the very edge of this cone, defining the absolute limit of the cause and effect. It's the messenger that weaves the cosmos together, yet, for the messenger itself, the message is delivered instantly. We started this journey seeing the world through our own eyes, a world of solid distances and steady, reliable flow of time. We saw how a single, strange fact, the unchanged speed of light, forced us to tear down that comfortable reality. We followed Einstein's logic to stunning conclusion that space and time are malleable fabric that stretches and shrinks with motion. Finally, when we look on the perspective of light itself, we saw the entire universe collapse. For a photon, there is no yesterday, there is no tomorrow. There is only one single timeless instant. There is no here and there. There is only a single dimensionless point. The light from the most ancient star you see in the night sky traveled for billions of years and across quadrillions of miles to reach your eye. But for that light, the journey was over the very instant it began. From its perspective, it was born and died in the same moment, right where you are standing. What is the shortest possible moment of time? No, I'm not talking about millisecond or nanosecond. What if the universe itself has a fundamental, indivisible tick? An interval so ridiculously small that if you wanted to write it down, you would have to type a decimal point, then 43 zeros, and then 539. At this impossibly tiny fraction of a second, our entire understanding of reality starts to fall apart. Space and time might dissolve into chaotic bubbling sea of possibilities. This is the story of Planck time, the ultimate wall our theories have slammed into. It's the story of the moment our physics just breaks. To really wrap our heads around the mind-bending smallness of Planck time, we have to go on a journey straight down from the world we know to a place so alien it breaks our intuition. We have to zoom in, way past everything we thought was small, and then just keep on going. Our journey starts with something we all know: 1 second. In 1 second, your heart beat once. A car on highway moves about 90 feet. For physicists, a second is a pretty comfortable, almost lazy amount of time. But we are just getting started here. Let's chop that 1 second into 1,000 pieces. Now we are at a millisecond, 1,000th of a second. Our world here is still pretty recognizable, just a whole lot faster. A camera flash lasts about a millisecond. A hummingbird can flap its wings every few milliseconds. It's quick, but our technology can keep up. It feels fast to us, but on the cosmic scale, it's an eternity. Now let's divide by 1,000 again. 1 millionth of a second. At this point, our human senses are completely left in the dust. To give you some perspective, a single microsecond is to 1 second what a second is to about 11 and a half days. You can't feel it, but this is the time scale where high-speed electronics live, the silent, lightning-fast world that powers our digital lives. But the universe is just getting warmed up. Let's go smaller. Divide by 1,000 one more time. Welcome to a nanosecond, a billionth of a second. This is where the example starts to get a little weird. In just 1 nanosecond, light, the fastest thing in the universe, travels about 1 foot. In modern computer, a single core operation can happen in a fraction of a nanosecond. We are now in a realm where the ultimate speed, the speed of light, becomes real, practical problem for designing things like CPU. It's hard to even imagine anything shorter than that. But we have to keep going. Divide by 1,000 again. We have reached the femtosecond. Now that's 1 quadrillionth of a second. At this scale, we leave the world of electronics behind and step into the world of chemistry. Chemical reactions, the very thing that makes life possible, happen at femtosecond timescales. The bonds holding molecules together vibrate and snap in just few hundred femtoseconds. The only way we can see things happening is with incredibly powerful lasers that shoot out pulses of light lasting just few femtoseconds, acting like a strobe of light for the dance of molecules. Surely, this has to be the end of line. What could possibly be smaller? Well, let's divide by 1,000 one last time in this part of the trip. We are now at the attosecond, 1/4 of a second. Now, this number is so fantastically small, it's hard to even process. An attosecond is to a second what a second is to about 31.7 billion years. That's more than double the age of entire universe. At this scale, we're not watching the whole atom anymore. We are watching the electrons themselves. The time it takes for an electron to do its thing inside the atom is measured in attoseconds. We are now watching the frantic, blurry quantum dance that underpins all of the existence. We have zoomed in a billion times from where we started. We have gone from a heartbeat to a computer chip to a molecule vibrating to an electron zipping around. It feels like we have hit the rock bottom. But we haven't. We have to go even further. We have to keep dividing, not by 1,000, not by million, but by a number so huge it's even hard to name. Something like million, trillion. Down, down, and down we go, past the limit of our tools, past the thing we can actually measure, down into a place where physics, our very concept of space and time, starts to unravel, down until we hit a wall, a fundamental barrier. We have arrived at the Planck time. So the Planck time is about 5.39 times to 10 to the power of negative 44 seconds. That's the number we talked about at the start, a decimal point, 43 zeros, and then 539. It's a number so outrageously close to zero, it's hard to see why it isn't zero. But that tiny difference is one of the biggest mysteries of physics. Trying to put this into perspective is almost impossible, but let's give it a try. There are more units of Planck time in a single atom than there are seconds in the entire 13.8 billion year history of our universe, and even way more. Now, this isn't just some random tiny number. The idea is that it might be the fundamental limit. Some theories suggest that it's the shortest possible unit of time that can even exist, the single indivisible tick of the cosmic clock. In this version of reality, the very concept of time below this scale might be meaningless. You couldn't have something happen in half a Planck time, just like you can take a half step if you're walking on a path made of single brick. It would be the fundamental pixel of time itself. But why? Why can't we go smaller? The answer seems to lie at the massive collision between our two greatest theories of physics: general relativity, Einstein's theory of the very big, and the quantum mechanics, our theory of the very small. Now, there's a great thought experiment that shows the problem. Imagine you want to measure an incredibly short sliver of time. To do that, you need a very precise clock. In physics, to measure something really small, you need a ton of energy. To look at the time down to a Planck scale, you would have to cram an immense amount of energy into an impossibly tiny point in space. According to quantum mechanics, that's totally fine. But according to Einstein's general relativity, that's a recipe for disaster. General relativity tells us that if you concentrate enough energy or mass in one spot, you will wrap up the fabric of space-time so much that you would create massive gravity. It's like trying to measure how thick a soap bubble is by trying to hit it with a bowling ball. If you actually built a device precise enough to measure an interval shorter than Planck time, you would have to pack so much energy into it that its own gravity would cause it to instantly collapse into a microscopic black hole. Now here's the cosmic trap. The clock, the very thing you built to see that tiny moment, would be swallowed by its own event horizon. How would measuring anything smaller than Planck time create a black hole? Let me show you how. I've got this camera and the shutter speed as of now is 1/30. you'll see that as I increase the shutter speed, right, it gets darker and darker. That means that in order to take the picture of it, I need to illuminate this object with something else, another source of light probably. That means that I will require to put some energy into it. But how much energy exactly? Energy required will be equals to h bar divided by 2 multiplied by Planck's time. Now we know what is Planck's time, which is 5.39 into 10 raised to minus 44 seconds. That would mean energy will be 10 raised to 9 joules. Now that is 1 billion joules, 1 billion joules in a very small space. Now, if you look at Einstein's equation, which is E equals to mc squared, means mass will be energy divided by c squared, and plug this to Schwarzschild's radius equation. You'll get a black hole as big as 10 raised to minus 35. Means if you're trying to measure time lesser than that, you'll get a black hole and it'll swallow everything within this range. Any attempt to see what happens in the span shorter than that, than the Planck time, seems doomed to fall, because the very act of looking would create a black hole that eats the entire experiment. Now, this is the wall, a fundamental wall. It doesn't seem to be a technical problem that we cannot solve. It seems to be the fundamental rule built into the fabric of reality itself. At this scale, the smooth, continuous sheet of space-time that Einstein described is believed by some to break down completely. If you think of space-time as a calm, glassy lake, then at Planck scale, it becomes a chaotic boiling frenzy, a concept called as quantum foam. Imagine that if you could zoom in all the way to Planck scale, you would see tiny particles and macroscopic black holes constantly popping in and out of existence, churning up space and time like boiling water. In this world, before and after might not even mean anything. The steady flow of time would just dissolve. This isn't just where our clock breaks, it's where our whole idea of time might not even apply anymore. So, where did this bizarre, reality breaking number even come from? It wasn't just made up. Planck time and other Planck units came from the mind of Max Planck, one of the founders of quantum theory, all the way back at the turn of 20th century. And here's the kicker. He wasn't even trying to find the smallest moment of time. He was looking for something he thought was more important, the set of natural unit. You see, physics is built on fundamental constants, these numbers that seems to be same everywhere in the universe, the basic setting of our reality. Planck realized by combining these three most important constants in a very specific way, he could come up with units for things like length, mass, and time that weren't based on random human things, like how long a king's foot was, but on the universe itself. These three ingredients are like the holy trinity of physics. First, you have got c, the speed of light in vacuum. This is the ultimate speed limit in the cosmos, the constant that links space and time together. It's the star of Einstein's relativity and the cosmic law that says how fast anything can travel. Second, there is g, the gravitational constant. This number sets how strong gravity is, the force that shapes the entire galaxies and keeps our feet on the ground. G is the universe's grand architect, the main player in general relativity. Third, you have h bar, the reduced Planck constant. This is the fundamental constant of quantum mechanics. It's the number that defines how pixelated the universe is, telling us that the universe comes in little packets or quanta. If G is the architect of the big stuff, h bar is the rule of the weird random world of the very small. Planck discovered there is only one way to mix these three constants, c, g, and h bar, to get a unit of time. The formula is the square root of h bar times g, all divided by c to the fifth power. Think about what that means. It's a recipe written in the language of universe. It takes the law of the very fast, the law of very massive, and the law of very small and mashes them all together. Planck time is the point where these three huge domains, relativity, gravity, and quantum mechanics, all crash into each other. And that's exactly why our physics breaks down here. Our current understanding of the universe is split between these two amazing but totally incompatible theories. General relativity perfectly describes gravity and the huge scales of the universe. Quantum field theory perfectly describes other forces and the subatomic world. It's like having two master rule books for reality, but one for giant and the other one for the ants. And their rule contradicts each other right at the scale where giant and ants are the same size. At Planck scale, you would need both rule books. You need a theory that can handle quantum nature of gravity itself. We don't have that theory yet. Finding it is arguably the biggest challenge in physics today. It's a giant neon sign pointing right at the edge of human knowledge, screaming, beyond this point, you're going to need a new map. The idea of a Planck scale isn't just a puzzle for physicists, it has huge implications for how we understand the most extreme places in the universe, the very beginning of the everything, and the dark heart of a black hole. Let's rewind the clock 13.8 billion years to the Big Bang. We can describe universe when it was million years old, 1 year old, even 1 second old. But as we get closer and closer to zero, we hit that wall. We arrive at what's called as Planck era. This is the slice of cosmic history from the very beginning up to one Planck time later. Our physics has no clue what happens in that moment. One entire observable universe was crammed into a space smaller than a single atom, at an energy that's impossible to imagine. The four forces we know today were probably all merged into one single superforce. So, what was the universe like before one Planck time? The honest answer is we have no idea. The question, what happened before, might not even make any sense, since the time itself, as we know it, may break down at this scale. There might not be even a before. Asking what came before the Big Bang would be like asking what's north of the North Pole. Time may have actually emerged from the timeless, spaceless state that is completely beyond our imagination. Now let's jump from the beginning of the time to a place where the time is set to end, the singularity inside a black hole. According to general relativity, singularity is a point of infinite density and a zero size, another place where our equations just give us nonsense, like a calculator trying to divide by zero and giving us an error message. But a lot of physicists think that a theory of quantum gravity will save us from this idea of infinity. One popular idea is that singularity isn't infinitely tiny point at all, but a region that is about Planck scale, a super dense nugget of stuff that's governed by the unknown laws of quantum gravity. Instead of being an end of the road for reality, is just another spot where our current map runs out. This all leads to one of the most brain-melting questions of all. If there's a fundamental Planck scale, does that mean that time itself isn't a smooth flowing river, but more like a series of individual discrete frames? Is reality basically a movie playing out one Planck scale moment at a time? This is the key idea in some theories of quantum gravity, like loop quantum gravity. This theory suggests that the fabric of space isn't continuous, but actually woven from a network of tiny, indivisible loops. In this picture, space itself is made of atoms of space, and time isn't some master clock ticking in the background. Instead, what we call time is just another measurement of how quantum bits of space change in relation with each other. If that's true, then our perception of time as just smooth, unbroken flow is just an illusion, an effect that emerges from the fundamentally choppy and pixelated reality. It's like how smooth surface of water emerges from the chaotic jostling of countless individual H2O molecules. The smooth flow of time might emerge from the frantic evolution of quantum reality. We started with a simple question: what is the shortest possible moment of time? And that question has taken us to the absolute limits of what we can understand, to a scale so small it's hard to imagine, and to a wall where our best theories of universe just collapse into paradox. The Planck time is more than just a number. It's a frontier. It represents the boundary between what we know and what we don't, because the universe we can describe and a deeper reality we are only just starting to get a peek at. It teaches us that smooth, predictable world we experience might be one giant, magnificent illusion built on chaotic, quantized and utterly strange foundation. At this tiny moment, 10 raised to negative 44 seconds, our physics as we know it breaks. But this isn't an ending, it's a beginning. It's a promise, it's a signpost pointing the way toward a new, more complete understanding of the cosmos. A theory of quantum gravity will finally unite the world of the very small and the world of the very large, and maybe finally explain the true nature of space and reality of time itself. A photon is born in the fiery heart of a distant star a million light years away. It races through the freezing darkness of intergalactic space, slipping past the gravity wells and drifting clouds of dust. And after traveling for a million years, its journey ends where it strikes a single cell in your eye. For us here on Earth, that's a story with a beginning, a middle, and an end, a journey that took millions of years. But for the photon, that entire epic, a million years of cosmic wandering from our perspective, happened exactly in zero time. From photon's point of view, the instant it was created is the exact same instant it was absorbed. It experienced no journey, it crossed no distance, and it felt no passage of time. It was born and it died in the very same moment. This isn't a philosophical riddle, it's a direct consequence of the laws of physics that govern our universe. It's a truth so profound and so alien to our experience that it forces us to ask a terrifying question. If the fundamental particles that make up our reality don't experience time or space, are time and space even real? Or are they just stubborn illusion we all share? Today, we are going to the edge of reality, to a place where time and space break down, to ask, what is universe really made of? To see how a million-year trip can happen instantly, we have to jump back to 1905. A young patent clerk in Bern, Albert Einstein, released a paper on special relativity. It rested on two ideas that sounded simple but changed everything. The first one is easy enough to swallow. The laws of physics are same for everyone moving at a constant speed. If you are on a perfectly smooth train and you drop a ball, that ball falls straight down, just like it would if you were standing on the ground. Simple. There's no special master reference frame in the universe. But it's the second idea where things get weird. Einstein proposed that the speed of light in a vacuum, the cosmic speed limit of roughly 299,792 km per second, is same for everybody. It doesn't matter if you are standing still or racing towards the light source in a spaceship nearly at the speed of light. When you measure that speed, the speed of light, you will always get the same exact number. Now hold on, this should feel wrong. We are used to adding up speeds. You drive at 50 kilometers per hour, you throw a baseball at 50. To someone standing on the side of the road, the ball is moving at 100. Simple, 50 plus 50. But light doesn't play by that rule. Turn on a flashlight in that same car. The person outside doesn't see the light moving at your speed plus its speed. They see it moving at exactly the speed of light. And here's the weird part. You sitting in that car also measure it moving away at exact same speed. This one rule cannot be broken. If everyone must agree on speed of light, then something else has to bend. And what bends is time and space. They're not solid, fixed stage Newton imagined. They are flexible, they stretch, they warp, and they depend on who's watching. My time isn't always your time. And that's our first clue to why photon doesn't experience time at all. To really get our heads around this, we don't need complicated mathematics. We just need simple thought experiment, the light clock. Imagine a clock made of two parallel mirrors. A single photon bounces between them. Every time it hits the top mirror, the clock ticks. If this clock is sitting in front of us, the photon travels in a straight path up and down. The distance is fixed, the speed of light is fixed, so ticks are perfectly regular. Tick-tock. Now let's put that clock on a spaceship flying past us, say at 80% the speed of light. From our perspective, the clock is moving sideways. For the photon to get from the bottom mirror to the top, it now has to travel a longer diagonal path, because the top mirror has moved by the time it gets there. Remember Einstein's rule, the speed of light is constant. We, the stationary observers, still see that photon moving at the speed of light. But we also see it traveling a longer distance for each tick. If speed equals to distance divided by time and the speed is constant while the distance has increased, there is only one possible conclusion: time itself must have increased. From our perspective, the moving clock is ticking slower than our own. Time for that spaceship has slowed down. This is not an illusion, it's a real measurable effect called time dilation. Astronauts on International Space Station are moving faster than us, so their clocks tick ever so slightly slower. GPS satellites orbit at even higher speeds, and their clocks still have to be constantly corrected for the time dilation. If they weren't, your GPS would be off by several kilometers every single day. Both Voyagers are moving away from us at an astonishing speed, so its clock is running slower. The faster you move through space, the slower you move through time. So what happens when you push this to the absolute limit? We have seen that as you approach the speed of light, time dilation gets more and more extreme. But a photon isn't approaching speed of light, it is at the speed of light. It has no mass, so it travels at the cosmic speed limit, c. So what does math say happen at v equals to c? It gives a clear, unambiguous answer. At that exact speed of light, time doesn't slow down, it stops completely. For a photon, time doesn't pass. From its point of view, now we have to be very careful using this phrase. There's no before or after. A photon doesn't have a rest frame, so it doesn't experience the time the way we do. The moment it is born and the moment it hits your eye are, for the photon, the same event. A photon that has traveled million years didn't age at all. Its entire journey happened in no time. Now, relativity tells us that space is just as flexible. As you approach the speed of light, the space in your direction of motion contracts. This is called length contraction. From your perspective, the universe shrinks. For a photon traveling at the speed of light, this length contraction is total. The distance between its start and the end point compresses all the way down to zero. That million-year journey, from photon's point of view, the distance between the star and your eyeball was zero. No time passes, no distance is crossed. For a photon, the entire universe is a single point, experienced in a single instant. If your mind is spinning right now, good. That means you are paying attention, and we are just getting started. What we have discussed so far is agreed upon and experimentally verified physics. But this conclusion that photons are timeless and spaceless is a doorway to a much deeper question. If you're enjoying this trip into the bizarre nature of reality, help me out and hit that subscribe button. It tells the algorithm that big ideas are worth spreading. Now, let's get weirder. We have reached something profound. The very particles that carry light don't live inside time or space. That should make us stop for a moment. We usually picture space and time as foundation, the stage the universe is built on. But if the actors on this stage don't follow the rules, maybe the stage isn't as solid as we thought. This brings us to one of the biggest mysteries in physics. Our two best theories don't agree. On one side, you have general relativity, a theory of the very large. It treats space-time as a smooth fabric. Mass and energy bend that fabric, and we feel that bending as gravity. And we have tested this over and over. We have seen massive spinning objects, including Earth, twisting space-time itself. That effect has a name: frame dragging. On the other hand, we have quantum mechanics, which describes the world of the very small. It's a world that is grainy, probabilistic, and weird, where particles can be in multiple places at once. Both theories are incredibly successful, but when you try to merge them to describe the gravity of a single particle or the inside of a black hole, the math breaks and spits out nonsense like infinity or divide by zero. This tells us that our understanding is incomplete. We are missing a deeper theory of quantum gravity. And a radical idea in the search for this theory is that space-time isn't fundamental at all. It's an emergent property, a large-scale illusion that arises from a deeper, stranger, and fundamentally spaceless and timeless quantum reality. But what is an emergent theory? Just as the wetness of water is an emergent property of trillions of H2O molecules, a single molecule isn't wet. Maybe space-time is what quantum mechanics looks like at our scale. So if space-time isn't truly fundamental, what is it made of? What's underneath it? A growing number of physicists are exploring a wild idea: quantum entanglement. You may have heard of it. Einstein called it spooky action at a distance. It's when two particles become so deeply linked that measuring one instantly tells you something about the other, no matter how far apart they are. Now, this is going to confuse you. There's a bold idea called ER equals to EPR. It suggests that this spooky link is actually geometry of space-time. In other words, two entangled particles might be connected in a tiny wormhole, an Einstein-Rosen bridge. If that's true, then space itself may not be something that exists first. Instead, space could emerge from these quantum connections. The more of these two things are entangled, the closer they are, not in ordinary distance, but in the structure of reality itself. In this picture, the universe isn't sitting inside a container, the universe builds a container. Our 3D world might be a hologram, a projection from a deeper layer of quantum information where distance, as we know it, doesn't even exist. Another radical theory called loop quantum gravity paints a different but complementary picture. It suggests that if you could zoom in on spacetime to the tiniest possible scale, the Planck scale, you'd find that it's not smooth at all. Instead, you'd see that spacetime is made of discrete, indivisible units, like pixels of reality. As per this theory, space is a network of interconnected loop, a chaotic structure often called as quantum foam. Time doesn't flow like a river, it ticks forward in indivisible steps. In this world, there is no in between. The very concept of continuous space and time dissolves into a granular, more fundamental reality. Our smooth universe could be just a large scale average of these quantum loops. This leads us to a fascinating, if speculative, new metaphor for reality: the blockchain universe. Imagine every quantum interaction, every event records a transaction in cosmic ledger. This act of creating an irreversible entanglement is what we experience as a moment of now. The past is simply the set of all recorded blocks on the chain, fixed and unchangeable. The future is an open space of all possible transactions that haven't happened yet. And the arrow of time is nothing more than the process of the ledger growing, one quantum event at a time. Spacetime emerges from the patterns of information in this cosmic data structure. So back to that question, what is reality made of? Our journey started with a strange fact about a photon. We saw how relativity forces us to accept that for light, time stands still and space disappears. But that wasn't the answer. It was the loose thread that, when pulled, starts to unravel entire picture of reality. That thread led us from the established physics to the speculative frontier of quantum gravity. We have seen how spacetime itself may not be fundamental, but an emergent illusion. An illusion woven from the spooky threads of quantum entanglement, an illusion built upon the pixelated quantum foam, an illusion perhaps best described as a cosmic ledger, where the arrow of time is simply the irreversible recording of reality. We live our lives on what feels like a solid stage, the stage of reality, but the science is pointing towards a shocking possibility, that the stage of reality itself is woven from the actors, that our universe of location and duration is a grand-scale effect of a deeper, timeless and spaceless quantum world. The very light that allows you to see this world may not truly exist within it, and the thought is where the next revolution in physics begins. So what do you think? Is spacetime the bedrock of reality, or is it a beautiful illusion generated by something deeper? Let me know your thoughts in the comments below, and if you want to keep exploring the biggest questions in the universe, make sure you're subscribed with notification on. Thanks for watching.